This is WK2.I. We're going to look at stopping distance for a car when it's skidding to a stop, and we're going to look at it in a way that first examines it in a qualitative way and then asks us to justify that qualitative analysis with a quantitative approach. It's called a qualitative-quantitative linkage. And we want to be able to show quantitatively why what we describe qualitatively is supported. All right, so car is moving with mass m. It's got an initial velocity of v0. And at some time, the driver fully applies the brakes. The car's wheels lock. Okay, so we're in a skidding scenario. And the car slides a distance capital D, and the coefficient of friction between the tires and the roadway is mu sub k. So this is a kinetic friction example because we have a skidding tire on pavement. One thing we can go ahead and note on the sketch is that the acceleration is in this direction. The car is slowing down, so we would expect the velocity and the acceleration vectors to be pointed in opposite directions. So if our acceleration vector is pointed to the left, then we would expect our sum of forces in our force diagram to also be pointed to the left when we're all done. So the first thing we want to do is we want to go ahead and draw and label those forces. So we've got the force of the earth on the car. We want to draw a normal force that is in the opposite direction, that is equal in size because those forces are canceling out. And we've got kinetic friction. Which direction is kinetic friction going to point? That's the only other force acting on this car. So if I've got acceleration to the left, it should be obvious that I need my frictional force to be pointed to the left as well. And I'm going to label this little f sub k to denote kinetic friction. Again, point this out numerous times that these two vectors, the normal force and the frictional force, are really two components of the same force, the force of the surface on the car. And even though they are components, again, there's some dispute in the Physics 1 community that this is okay for this situation to actually draw the components of the surface force. So don't be confused if you see that. The book kind of uses a bit of a different language to describe this. All right, so let's analyze this symbolically. There's no numbers at all. We've got to be able to deal with just simply qualitatively examining this without numbers. The stopping distance d depends on the initial velocity and the coefficient of kinetic friction. Does the value of d increase or decrease with increasing initial speed v0? Give a physical explanation why this is the relationship. Now, we don't want to be breaking out formulas at this point, but you need to be able to put a well-constructed chunk together with concrete details that start from observations or given information and drive you to a conclusion. So let's just build an argument here. So let's start with something in the information, maybe from the force diagram. So the frictional force is causing the acceleration. Okay, and so let's now start to state some things that are always true. F sub k, F sub k does not change with speed. Remember that kinetic friction is the same regardless of what speed you are traveling at. So it doesn't really have any relationship to v sub 0. So the acceleration does not change as the velocity v0 is increased. So I'm linking concrete details together here using things I'm given, things that I'm sort of moving towards as I move towards a conclusion about the stopping distance d. So now I've claimed that the acceleration is the same regardless of the initial velocity. So I feel like at this point I can go ahead and jump to my conclusion. It will take a longer distance to come to a stop with the same acceleration. Now that may be a bit of a leap of logic. So we might want to actually even throw in a kinematics formula to support it, although we don't want to dive into it too much. So we could just simply state what the formula is that would be best applied here. So the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. Okay, so that's a kinematics formula that you could pretty quickly apply and recognize that if the final velocity is 0 and this term is getting bigger, this term has to get bigger in the opposite way if this side of the equation is 0. So if this is going up, this term has to go down. But if acceleration is the same, that term has to get bigger. Because remember, the acceleration is negative. So that's where the negative term comes from. But okay, I completely messed that up. Let's start that over. Let's start that explanation over. So the final velocity is 0. And this term is getting larger as we look at increasing velocities. Acceleration is negative because it's in the opposite direction. So to balance out a term that's getting bigger, the displacement has to get bigger as well. Another way to look at that might be with a velocity time graph. And remember, the area under the curve of velocity time graph is going to be the displacement. So if we start out with this velocity and we accelerate to a stop, then this is our displacement during the stopping time. Whereas if we start with a higher initial velocity, apply the brakes at the same time and with the same acceleration, then this is our stopping distance, the area under the curve. Obviously the green triangle is bigger than the red triangle, so as initial velocity increases, then the stopping distance is going to increase. Again, this is more, I'm saying this all to more help you support it in your mind, not necessarily with a qualitative description. What I wrote here in red, I think, is a sufficient qualitative description. So let's now analyze, how does the value of the stopping distance change? Oh, it's always good to check. How does the value of the stopping distance increase or decrease with increasing coefficient of friction? So now if mu sub k goes up, then is our stopping distance going to increase or decrease? So in this case, the frictional force again is causing the acceleration, we're noting that from the force diagram, F sub k depends directly on mu sub k. In other words, there's a direct relationship between the two. So if mu sub k increases, F sub k will increase. And acceleration will also increase. So let's make the claim. If the acceleration increases, the distance, the stopping distance will decrease. All right. And again, if you want to throw in a kinematics relationship, although you don't need to go in and analyze it, the one that I would simply choose would be simply delta x. I would choose actually essentially the same one. It would be the same one. V sub f squared is equal to v0 squared plus 2a delta x. So again, this starts at 0. This is a constant. It's not changing. So if the acceleration is going up, the stopping distance must go down because we need those to be equal to always be equal to v sub 0 squared. If you want to look at it on a velocity time graph, we have the initial velocity with that acceleration and that stopping distance, and we have the same initial velocity but a greater acceleration, so a steeper slope. And so this triangle represents, again, the displacement during that time. Obviously the green triangle is smaller than the red triangle, so increasing mu sub k will cause a decrease in the stopping distance. So I wanted to explain the physics to you. Again, I've used a lot more words than you really need. Just what is written in red would be sufficient. All right, now we want to take a look at it from Newton's second law and be sure that we can show the same thing. So derive two equations, one in the y, one in the x, expressing Newton's second law using the symbols that are given and physical constants that are appropriate. Okay, we're going to explain. They want you to explain what you're doing in each line, but again, I'm not necessarily going to write that out. So from our force diagram, the only thing we haven't really done is define coordinate systems. So we'll call that direction x, positive to the right, and positive y is up. So we've already been given the first line of Newton's second law for the y dimension, so let's go ahead and start there. We've described the normal force in the positive direction and the force of the Earth in the negative direction, and that's going to be equal to mass times acceleration in the y. The acceleration in the y is equal to 0 because it's not accelerating up and down in the vertical direction. So the normal force minus the force of the Earth is equal to 0. And the normal force is equal to the force of the Earth simply just by algebra rearranging. And we could take one more step and say, hey, the force of the Earth is equal to m times g. So now we've gotten the y equation as far as we can take it. So let's go ahead and work on the x equation. Sum of the forces in the x is equal to mass times acceleration in the x dimension. we've got one force that's acting, and it happens to be in the negative direction. And we've already defined what the acceleration is with a little letter A. What is the force of friction? Well, it's a kinetic friction. Probably should not use that since I used that in my force diagram. That would be a better way to describe it. F sub k. Whoops. What is the kinetic force of friction? Well, we know it's mu sub k times the normal force. And that needs to equal mass times acceleration. And now that I have got an x equation as far as I can take it, I can start combining these two things together. So I note that I have a normal force here, and I've got a normal force here. So the next step would be to combine the y equation into the x equation. So I'll simply combine those two together and say that minus mu sub k is equal to m times mg is equal to m times a. And then I can take this one step further and eliminate the m's and solve finally for the acceleration. Put the acceleration on the left is equal to minus mu sub k times g. There we go. So the acceleration, so if we want to just examine this real quick, the g we know to be 9.8 newtons per kilogram. We know that mu is going to, typically be a number between 0 and 1. And we're going to multiply by a negative sign. And so our answer is going to be somewhere between 0 and 9.8 meters per second squared, and it's going to be in the negative direction. And that would make sense because I have defined negative in the leftward direction. That's the direction that the force is applied. That's the acceleration we would expect, so we get a negative answer. That's what we would expect. Okay. Now we get to the quantitative analysis where we want to link what we said back here in part B with a quantitative analysis of this. We're going to look specifically at how D again relates to V0 and mu sub k, but we want to get there quantitatively. So this is a derive, first a derive, and then a explain. So we want to derive first what that relationship is, and then we want to see if it matches our qualitative analysis. So write an equation for D. This is a derive. They say write, but it's really a derive. Whenever we derive, we always want to start with one of our basic formulas. So this kinematics formula that I used before is the best place to start with this particular one. So you want to essentially write that equation, the base equation that would come off of a formula sheet, and then you want to plug in, sort of link it back to the specific variables that they have in the equation. So start there. What's the final velocity? Well, the car comes to a stop, so the final velocity is 0. The initial velocity, well, the initial velocity actually has the same name, so we don't need to change that. The acceleration, well, we know what the acceleration is now. The acceleration is minus mu sub k times g. So let's go ahead and plug that in. Minus mu sub k times g. And the change in position, well, that's going to be the stopping distance, d. And we want to derive an equation for D. So let's go ahead and solve this for D. So I can move this to the other side of the equation. 2 mu sub k g d is equal to v0 squared. And then I'm running out of room, so I'll move over here. D is equal to v0 squared over 2 mu sub k times g. So I've derived an equation for D. It's in terms of v0, g, and mu. So that's a derive. Started with a formula right off of the formula sheet, and I've solved it for the thing in question, D. Now, explain. Let's link this back to what we said in part B. Let's remember what we said in part B. As v0 goes up, D will go up. As mu sub k goes up, D goes down. So let's look at this equation. Does this support what we said? Okay, so V0 is in numerator. As it increases, D will increase. There we go. And then similarly, mu sub k is in denominator. As it increases, D will decrease. So we've analyzed the quantitative relationship, and we've linked it back to what we said before. We can even make that claim. This matches what was stated in part B. Okay, so that is what is known as a qualitative-quantitative analysis, and that is a skill that you need to be able to have.